Before we jump into today's new topic, which is allowable stress and safety factors, I want to quickly review the two kinds of stresses that we've used so far in this class. The first is what we call normal stress. We calculate normal stress. It's the Greek letter lowercase sigma. It's equal to the normal force N divided by the cross-sectional area. So the picture I want you to think of whenever you see this normal stress is if there's a normal force pulling on a bar of some kind, and we go and cut it open and draw a free body diagram where we expose that cut face. What happens if I draw that little free body diagram is I still have N acting overall on it, but on that cut face, we tend to think of that normal force as being kind of spread out uniformly all over the area, and that magnitude is what we're calling normal stress, sigma. And the units for this are either pascals if we're dealing with newtons and meters, or psi if we're dealing with pounds and inches. There's a principle that's worth bringing up now, and it's based on a mathematician named Saint-Venant. French name. What this principle says is that if I'm looking at the actual stress distribution, right? You see how I just drew it here as being totally uniform? We just took the total force, divided by the area, treat it like it was the same everywhere. What Saint-Venant says is that that's actually a really good estimate when you're a long way from a point load, right? My point load's all the way here at the end of my long slender bar. If I cut it in the middle, that stress will be pretty much exactly uniform. However, if I cut it really close to the end, the stress distribution, if this is a true point load being applied right smack dab in the middle, the stress distribution probably won't be uniform if you're really close to the point of load application. Saint-Venant tells us we should treat that stress as uniform as long as we're not right at the end. This is a principle rather than an exact quantitative thing. So assuming the stress is uniform over the entire bar is typically a good assumption for long, slender bars. And again, it's a principle, so we're going to say we want the length to be bigger than probably 10 times the diameter, approximately. We'll sometimes use it for shorter, less slender bars, but it tends to become a better and better assumption the longer and more slender those bars are. The other stress that we've dealt with so far this semester is average shear stress. For that, we use a Greek letter tau, lowercase tau, and it's equal to the shear force divided by the area. So we're going to use this for pins, like when we have a truss or something else that's pin connected. And the idea is that if I draw just the little pin that's inside my structure, right? Say I had a truss supported by a pin right there. What I'm doing is I'm zooming in on the pin. The pin would be pointed straight out of the page right there at it. And if I cut right through that pin that's being loaded up with a force, let me draw the force on here. So if my pin's being loaded with a force in that direction and a force in that direction, I cut it open, what I end up finding is that V is equal to F if it's set up in single shear, like this picture, versus a double shear situation. For double shear, we typically have a force acting to the right, and it's countered by a pair of forces F over 2 pulling back to the left. We end up with V equaling F over 2. Or double shear. And you would get that by cutting in between any two of these forces and finding out that V across this little cut open surface area would be F over 2 for double shear, and it's only going to be F for single shear. So those are the two things that we've dealt with so far with stress. What we're going to do today that's new is we're going to talk about this in terms of allowable stress and safety factors. So this is the first time that we're going to be able to start to predict whether something will fail and start to design based on material property information. So what we're doing with allowable stress, sigma allow and tau allow. These guys are our allowable stresses. That is the largest stress that the design is going to allow. It's not the stress that's going to cause it to fail. This is the biggest we ever want our part to see, because we probably don't want things to break, but we also don't want to get so close to breaking that we start to be nervous about it. So this is going to be the maximum stress that's allowed by our design. We get another pair of stresses. These are what we call sigma fail, normal stress that would cause failure, and shear stress that would cause failure. These are actual material properties. So whether we're dealing with steel, aluminum, wood, polyester, polypropylene, whatever the material happens to be, there will be failure values that you can look up for that material. And we'll have a whole chapter on material properties later on where we're going to get into should you use a yield stress or an ultimate strength, ultimate tensile or compressive strength or shear strength values. So these things are going to come from a table lookup. And they're going to tell you when that material is actually going to break. So if we reach either of these, the material will fail. They're the actual failure values. This means when it will break. We're going to design to these values knowing that these are the values where it's going to fail, and they're related by what we call a factor of safety. Our book uses FS to mean factor of safety, and the way we calculate it is we take the stress, either sigma or tau, that would cause failure and divide it by what we're actually going to allow our part to see. Okay, you could also calculate it as shear stress that would cause the part to fail divided by the allowable shear stress. And you see, since the number on top, the failure value on top, is the biggest the stress could ever be, it's going to break at that point. The number on the bottom has to be smaller, which means factor of safety must be greater than 1.0. And depending on your application will determine how big of a safety factor do you use. There are some applications where you might use a pretty small safety factor, just a little bigger than 1. Maybe you can't spare a lot of extra weight, and so you want to be just safe but not throwing a lot of extra material into it. Or maybe you're dealing with something, it could be catastrophic if it were to fail. So maybe you need a really big safety factor, like 3 or 4 or 5. Depends on your field that you're in, depends on your application. Let's do an example. We have a bar that is being loaded by a distributed load, and it is pinned at B to a bar, which is pinned to the wall at C. And the bar itself is also pinned to the wall here at A. And we have some dimensions, 4 feet, 3 feet, and 1 foot. We are told that all 3 pins are in double shear, and all 3 pins have the same diameter. We are told that the allowable shear stress in the pins is 12.5 KSI, because remember, when we have pins in double shear, we're going to be calculating shear stress, so we need an allowable shear. We are also told that the rod has a specific diameter and it has an allowable normal stress of 22 KSI. And then what it asks us is, with all of these design constraints, right, whatever material that this is made out of has to have a bigger failure stress than both of these. So somebody has already taken what the material is into account, figured out the failure stress, applied a realistic safety factor, and told us we need to make sure we never exceed these allowable values so that we maintain our safety factor. And so we're solving for the maximum value of the distributed load. We're told how big the stress needs to be at the end, and we're supposed to back up and figure out what the loading was. So why don't we solve it the way we normally would? Start with a free body diagram, write equilibrium equations to solve for forces. We can't actually get a number for them right away, but we'll be able to get an expression for how the force in member BC is related to W. And then we can maybe use these tau allow and sigma allows to figure out the max W. So free body diagram. And what should we draw the free body diagram of? Well, there's only 2 things. We've got this horizontal bar that has our loading on it. That's probably a good candidate. And then can you see that the BC is a 2-force member? It's a good old classic bar that's just pinned on the ends and it has no forces on it. It's a 2-force member, so we don't need a diagram of it. We know that it's just going to be in either tension or compression. So we'll just draw a free body diagram of the bar. It has our distributed load acting on it. I like to draw them with a little dash line and then replace it with its equivalent force. So at the middle, remember how to figure out distributed load? I'm going to take the area underneath that curve, and that is how big the load is. So the height of that rectangle is W, and the length of it is 4 feet. So the magnitude of this force is going to be W times 4 feet. W would have units of pounds per foot. So when you multiply by 4 feet, you get just pounds. So there's W. And now to draw a free body diagram, you remove supports. So we removed the support at A. A was just a basic pin. So at a generic pin, I always draw an AX and an AY. I usually draw them right and up. You want to draw them down and left, go for it. And now at B, we removed a 2-force member. So at B, I need to just draw on here the force in member BC. And the orientation of that will be the exact same as the orientation of member BC. It looks like it's on a 3, 4, 5 triangle. So we have the free body diagram with the bar. All I've done is removed a bar and a pin, so I replaced them with what they do to it. I converted the distributed load into an equivalent point load. Do you remember why it acts in the middle? Because that is the centroid of that rectangle. Since the rectangle is 4 feet long, this is going to act 2 feet over. And that little triangle is a 3, 4, 5, triangle. Up next, every time I draw a free body diagram, it is followed immediately by equilibrium equation. I am going to sum moments about point A because that is where two of my unknowns are, and then I will get a nice simple expression that will let me relate the force in BC to the distributed load. For moments relative to point A, if you have to come over to the right and then down, that is going to cause a clockwise moment. I call that negative. We've got W times 4 feet is how big the force is, and now I have to multiply it by how far away it is, which is that 2 feet I drew on the figure. And then FBC has got a vertical component and a horizontal component. The horizontal component is directed right through point A, so the distance is 0, causes no moment. But the vertical component, I'm going to use my 3 feet distance. To get the vertical component, use the vertical side of the triangle, 4 divided by the hypotenuse. So I will have FBC times 4/5. That gives me the vertical component of the force, and it is 3 feet away from point A. And that one is, since I'm going to the right and then upward, that is going to cause a counterclockwise moment, which I'll call positive, set it equal to 0, and I get FBC is equal to 3.33 feet times W. And the reason the feet are there is because of the units mismatch. F is going to be in pounds, but W is in pounds per foot. Now that I have that, I can sum forces in the X and Y direction. So if I sum forces in the X direction, I will have AX to the right minus 3/5 of FBC equals 0. Let's substitute in what FBC is equal to, and we get that AX is 2 feet times W. And finally, let's sum forces in the Y direction. I have AY straight up. Downward, I have got 4 feet times W, or W times 4 feet. And then I've also got plus 4/5 of FBC. That all has to sum to 0, and I get AY is 1.33 feet times W. We found expressions for all of the forces that we're going to need. Now, let's go back and look at what the question was asking. We've got 3 pins to look at. I'll do the pins in a minute. Let's first deal with rod BC. I have an expression for the force in rod BC, and I know that if the stress in that rod ever reaches 22 KSI, that is the most stress that I want that rod to ever see, because that is within my factor of safety that I want in my design. I want to set the stress in BC equal to the allowable normal stress. What is the stress in BC? Well, that's the force in BC divided by the area of rod BC. Okay, let's plug in some numbers. The allowable stress, 22 KSI. Remember, K is for kip, and a kip is 1,000 pounds. So this is 22,000 PSI. So on the left side of my equation, I've got 22,000 PSI. On the right side, I plug in what FBC is equal to, 3.33 feet times W, and then I divide it by the area, pi times the radius squared. The diameter of rod BC is 0.4 inches. Always remember to divide by 2 to get the radius. So times, it'll be 0.2 inches, and that gets squared. Let's see if the units are going to work out. Well, let me rewrite PSI as pounds per square inch to make this really clear. So then the inches squared on the bottom cancel the inches squared on the bottom right there. So we'll be able to solve for W, and W will be in terms of pounds per foot, which is a pretty typical way W is given in US customary units. Doing the math, you get W is 830 pounds per foot. So that might be the answer. That's a possible answer. That is the biggest distributed load before rod BC would reach its allowable stress. So let's go look at the pins next. I've got all 3 of my pins are in double shear, and they all have the same diameter, and they all have the same allowable shear stress. Can you see that pins B and C? Oh, they're attached to rod BC. So the force acting on those pins is just FBC. We can deal with those 2 pins at the same time. Pins B and C. Well, tau B is equal to tau C. We want to set it equal to tau allowable, and that's got to equal the shear force in pin B or C divided by the area of the pin. The allowable stress is 12,500 pounds per square inch, PSI, because it was 12.5 KSI. That's going to equal V of the pin. The pins were in double shear, so that means you're going to take the force acts on the pin. The force acting on this pin was going to be FBC. So this is actually equal to FBC, and I need to divide it by 2 because it's double shear. Let me say that one more. The force that's pulling on those pins from the bar is FBC. It's pulling equally on both pins in opposite directions. Because we're in double shear, we have to divide that force by 2. That will give us the actual shear force on the pin, and then I need to divide it by the area of the pin. So this will be equal to FBC, 3.33 feet W, Got to divide it by 2, and then on the bottom will be the area of the pin. It's circular, so pi times whatever its radius is squared. And these pins are smaller. They have a diameter of 0.3 inches. Half of that will be 0.15 inches. Okay, the units are going to cancel out exactly like they did before. I've got square inches in the denominator on both sides of the equation. Solving, I'm going to get that W is 531 pounds per foot. Another possible answer. So if W were to reach 830 pounds per feet, our rod will hit its allowable stress. If W hits 531 pounds per foot, then the pins at B and C both hit their allowable stress. I just need to check pin A, finish this problem. What do we know about pin A? Pin A is right there, and we drew this as having an AX and an AY, and then we solve for AX and AY separately. Well, I don't want the force at A in components now. All the pin cares about is what is the magnitude of the force? How big is it? First thing I need to do for pin A is figure out what the total force on pin A is. That's done using Pythagorean theorem, AX squared plus AY squared. Let me write it out. Inside here, I'm going to plug in my 1.33 feet times W squared plus 2 feet times W squared. And when you simplify that, you get 2.404 feet times W. That's the total force at A. So you remember shear force at A, this one's also in double shear. It's going to be FA over 2. So my tau at A, I'm setting it equal to tau allowable. It's the same as it was for the other pins, 12,500 pounds per square inch. That's got to equal V, which is F over 2. So 2.404 feet times W divided by 2 gives me the force. The area is just like what it was before, pi times 0.015 inches squared. Solving, we get W is 735 pounds per foot. So 3 possible answers. We've now figured out how big of a distributed load would cause each of these components of this structure to reach its allowable or design stress. There can only be one right answer, and the right answer is going to be this one. This guy right here is what governs the problem because it's the smallest. So you're never going to be able to get your distributed load all the way up to 830 or even 735 because the pins at B and C are going to be hitting their design limit first. So that's what governs, and so that is your answer. Let's do a couple of quick concept questions. What I have here, this is just a 2-dimensional picture. All of these parts extend into the page by some distance. The bracket here is just kind of, it's like it was a board that got machined down, so there's a little lip here so that you could hang a hook on it. We're going to ask a few questions. So question number 1, what is the shear force acting on the bracket? This is the actual bracket. What we want to do is, can you see that the shear force is going to be carried along a line of material right there? Anytime you want to find shear force is an internal force. So you're going to have to cut something open. And I'd really prefer not to ever have to find the reaction forces back here at the wall. So why don't we try just cutting along this little dashed purple line and do a little free body diagram. So free body diagram, cut at A. Got this little block sitting here. There's my cut open surface. The block represents this piece right here. And since I cut it open on that cut face, I want to draw a normal force, a shear force, and then a bending moment that way. There's probably got to be something else acting on it. Can you see that this part right here is going to be pulling down on it with 8 kips? So I also want to draw on here my downward applied 8 kip force. What I want to solve for is V. Summing forces in the y direction. I've got minus 8 kips minus V equals 0. So the shear force is minus 8 kips, or the magnitude of the shear force is 8 kips. Next question. So if the bracket is made from a material with a failure stress, tau fail, of 23 ksi, and we want a safety factor of 2.5, what is tau allow? All right, so this is going to test us on that safety factor definition right at the very beginning of class. Factor of safety, the equation is tau fail over tau allow. We're solving for tau allow. Well, that's going to be tau fail divided by the factor of safety. So that's going to be 23 ksi divided by 2.5. We get 9.2 ksi, and it should be smaller than tau fail. You would never want your allowable stress that you're going to allow every day on your part to be bigger than the failure stress. Third question, if the bracket has a thickness of 1/2 inch into the page, what is the required height H? So if into the page it is a 1/2 inch, how tall does it need to be in order to satisfy the design criteria? We now know tau allow, if that's our average shear stress, equals V over A. We know tau allow, we also know V. We calculated that before, so let's plug in what we know. I've got 9.2 KSI on the left. V is 8 kips, and then my area will be at my width into the page, 0.5 inches, times H. Solve for H. And what will happen with the units? I've got kip over inch on the right and kip over square inches on the left, so H will come out in inches. Solving, we get H is 1.74 inches. That's how tall we need that little bracket to be right there so that its average shear stress does not exceed the allowable stress when we apply 8 kips of force to it. That's the end of this set of notes on allowable stress and safety factors.